AndroCon, a novel ambient sensing method, harnesses semi-processed GPS data to create a sensor capable of accurately sensing the user's environment, recognizing human activity, and mapping indoor spaces. By leveraging information from GPS chips, including signal strength, Doppler shift, and signal-to-noise ratio, SNR, AndroCon enables Android applications to infer contextual information. A comprehensive study was conducted over a year, utilizing various mobile devices across a 40,000 square kilometers geographical region, including data collected from flights, cruise ships, and high-altitude locations. The study employed a multimodal approach, combining linear discriminant analysis, unscented Kalman filtering, gradient boosting, and random forest-based learning to accurately identify diverse scenarios. These scenarios included being inside a metro, a person waving a hand in front of the mobile device, being in front of a staircase, and the presence of people in the room. The results demonstrate the efficacy of AndroCon in expanding the scope of ambient sensing beyond traditional modalities like smart speakers, Wi-Fi signals, and mobile phone cameras. Notably, this research highlights the potential for location-based services to compromise user privacy. The findings emphasize the importance of addressing these concerns to ensure user privacy. By exploring the intersection of ambient sensing and location-based services, AndroCon contributes significantly to the field, providing a foundation for future research in mitigating privacy risks and developing more robust ambient sensing systems. Leveraging semi-processed GPS data, researchers have discovered a potential vulnerability in mobile devices, enabling an adversary to infer ambient context and user activity even when the device is in flight mode. By analyzing the GPS signals, an attacker can deduce various details about the environment, including whether the user is in a closed space or open area, crowded, moving quickly or slowly. To demonstrate this, the authors employ a nonlinear Kalman filter to clean the noisy GPS signals, followed by linear discriminant analysis, LDA, for feature reduction. The resulting data is then fed into a machine learning model for ambient and activity classification. The researchers also explore the use of semi-processed GPS parameters and signal strength, in conjunction with user trajectories and graph optimization techniques, to detect indoor layouts. This approach allows for the inference of floor maps and indoor layouts using semi-processed GPS data and user trajectories. The paper highlights 4 key contributions, characterizing the potential of semi-processed GPS signals for ambient sensing, demonstrating the ability to capture semi-processed GPS data without consent and utilize it to discern user ambience and activities, evaluating machine learning models to classify user activities and ambient settings using semi-processed GPS parameters, and inferring floor maps and indoor layouts using semi-processed GPS data and user trajectories. The Global Positioning System, GPS, relies on a network of satellites orbiting the Earth, transmitting radio signals that contain their location and time. The receiver calculates its geographical location by measuring the time delay between when a signal is sent and when it is received. However, GPS signals are susceptible to inaccuracies, including delays induced by the ionosphere, signal interference, and multipath effects. To account for these inaccuracies, modern receivers employ data cleaning techniques, such as the nonlinear Kalman filter. The authors present key equations to illustrate the relationships between satellite and receiver coordinates, including the calculation of distance between a satellite and a receiver, equation 1, and the Euclidean distance between satellite and receiver coordinates, equation 2. These equations are crucial in understanding the relationships between GPS signals and receiver coordinates, and the importance of accounting for inaccuracies in GPS signals. The researchers assume that the user has given an app precise location permissions, a common requirement for many e-commerce, ride-sharing, and gaming apps. However, this assumption may not be realistic in all scenarios, and the authors acknowledge the limitations of their approach, including the reliance on semi-processed GPS data, which may be noisy and require data cleaning. Future work could explore the extension of this research to other types of devices and sensor data. The GPS processing pipeline involves the transmission of multiple correction factors, including pseudorange, signal-to-noise ratio, phase shifts, Doppler shifts, and satellite details, to enable receivers to correct their data. The GPS message also contains receiver clock information. At the receiver, code and carrier tracking loops demodulate and identify incoming signals, calculate pseudorange, and aid in distance calculation. Modern GPS chipsets allow access to the pipeline, enabling the extraction of 9 semi-processed GPS data parameters, classified into 5 types: received signal power, carrier phase shift, multipath interference, signal-to-noise ratio, and Doppler shift. These parameters can be used to extract information about the surroundings. In Android, location accuracy permissions, such as access coarse location and access fine location, enable apps to specify desired precision and access device location. Access fine location, which utilizes GPS BASED positioning, requires higher precision and is necessary for accessing semi-processed GPS measurements. To address dimensionality reduction, the authors employ linear discriminant analysis, LDA, a supervised learning technique that projects a dataset into a lower dimensional space, enhancing class separability through a linear combination of features. LDA operates by finding a projection matrix that maximizes the between-class variance while minimizing the within-class variance. The authors also utilize the unscented Kalman filter, UKF, an advanced unsupervised technique for noise filtering in nonlinear systems. The UKF predicts the future state of a nonlinear system and updates this prediction using incoming noisy measurements. The UKF employs a deterministic sampling approach to generate sample points around the mean, accurately capturing the mean and covariance. This technique is widely used in fields such as robotics and navigation, where precise estimation in the presence of noise is crucial. The unscented transform, a key component of the UKF, approximates the state distribution using a set of sigma points, generating sigma points around the mean using the unscented transform. The GPS pipeline, as depicted in Figure 1, consists of signal acquisition, pseudorange calculation, satellite position calculation, and user position calculation, resulting in semi-processed data accessible to applications. Table I provides a comprehensive list of semi-processed GPS signal parameters, including pseudorange rate uncertainty, received signal time uncertainty, accumulated delta range, and carrier-to-noise density, among others. These parameters are crucial for accurate GPS positioning. The unscented Kalman filter, UKF, is employed to estimate the state of the system. The UKF algorithm involves 3 primary steps: sigma point generation, prediction, and update. Sigma points are generated using equations 5, 6, and 7, which involve the state estimate, error covariance matrix, and scaling parameter. The sigma points are then passed to the state transition function to generate a new set of samples, as described in equation 8. The predicted mean and covariance are computed using equations 9 and 10, which involve the weights for the mean and covariance, respectively. The predicted measurements are obtained by passing the sigma points to the observation function, as described in equation 11. The predicted measurements mean and covariance are computed using equations 12 and 13, which involve the weights for the mean and covariance, respectively. The innovation covariance is computed using equation 14, which involves the predicted measurement covariance and the measurement noise covariance. The Kalman gain is computed using equation 15, which involves the innovation covariance and the predicted state covariance. The state estimate is updated using equation 16, which involves the Kalman gain, innovation, and predicted state estimate. The error covariance matrix is updated using equation 17, which involves the Kalman gain, innovation covariance, and predicted error covariance matrix. The UKF algorithm is a powerful tool for estimating the state of nonlinear systems, and its application in GPS positioning is crucial for achieving accurate and reliable results. The semi-processed GPS signal parameters and the UKF algorithm are essential components of the GPS pipeline, enabling the calculation of accurate user positions. Limitations and assumptions of the UKF algorithm include the requirement for accurate models of the system dynamics and measurement processes, as well as the need for careful tuning of the scaling parameter and weights. Future work may involve exploring alternative algorithms and techniques for improving the accuracy and robustness of GPS positioning. The Kalman filter algorithm is a widely used technique for state estimation in dynamic systems, formulated mathematically through equations 12-14, which describe the prediction step. The predicted state estimate (ZT, t-1) is computed as a weighted sum of the previous state estimate and the process noise, while the predicted covariance (street) is obtained by propagating the previous covariance and adding the process noise covariance. The innovation step, described by equations 15-17, updates the state estimate and covariance based on the new measurement (ZT). The innovation covariance (quart) represents the covariance between the state and the measurement, and is used to compute the Kalman gain (KT). The updated state estimate (ext) is obtained by adding the product of the Kalman gain and the measurement residual to the predicted state estimate. The updated covariance (PT) is computed by subtracting the product of the Kalman gain and the innovation covariance from the predicted covariance. In the context of semi-processed GPS data, retrieved on an Android platform using the Android location genes measurements API, 9 parameters of interest are identified for feature selection, noise identification, data cleaning, dimensionality reduction, and machine learning model selection. The Doppler shift and carrier phase parameters are analyzed in detail. The Doppler shift parameter is used to identify motion state in environmental context, with high values indicating movement and low or near zero values indicating a stationary state or slow movement. The uncertainty in the Doppler shift measurement, denoted by pRU, varies with environmental conditions, increasing in crowded or mobile environments due to multipath effects and irregular Doppler measurements. The carrier phase parameter quantifies the accumulated error in the distance between the satellite and the receiver, with positive values indicating the satellite vehicle moving away from the receiver and negative values signifying the satellite vehicle moving towards the receiver. The carrier phase is used to differentiate between motion states and environmental contexts, with stable values in open areas and variable values in crowded or indoor environments due to reflections causing phase shifts. Analysis of semi-processed GPS signal characteristics reveals the intricate relationship between electromagnetic wave parameters and corresponding GPS parameters. This study explores the correlation among these parameters to demonstrate their potential for enhancing classification outcomes when fused. To achieve this, real-world data was collected using 5 different Android phones, including 2 identical models to assess variations across devices. The phones employed were the Redmi Note 9 Pro Max, Galaxy A54, OnePlus Nord CE2, and Redmi Note K20 Pro, with their specifications, such as Android version, chipset, and year of release, detailed in Table 2. Supplementing this data collection, the study utilized open-source datasets, specifically the Kaggle GNSS dataset, which comprises 39 traces collected using Pixel 4, Pixel 4 XL, and Xiaomi Mi 8 phones. This dataset primarily consists of measurements collected during motion. To generate supplementary data, the 5 phones were used to collect data at various sites, with each data collection process lasting approximately 45,150 minutes on average. Data was collected in diverse settings, including open grounds, indoors, while standing and sitting, to simulate real-world user activities and environments. Furthermore, to mitigate the effects of ionospheric electron density variations, weather conditions, and satellite position fluctuations, semi-processed data was collected 3 times over the course of a year under various atmospheric conditions and at different times of the day. Researchers have traditionally employed received signal strength, RSS, Doppler shift, and signal-to-noise ratio, SNR, to design human activity recognition, HAR, and ambient sensing systems for Wi-Fi, Bluetooth, and cellular tower signals. However, this study focuses on these parameters for characterization and calibration of the setup, mapping them to corresponding semi-processed GPS parameters, where the GPS signal inherently captures the automatic gain control, AGC, or signal power. The authors utilized an RF Explorer spectrum analyzer to record the signal RSS, which correlated strongly with the AGC, exhibiting a linear relationship with a correlation coefficient of 0.94. This finding was consistent across all data, including the Kaggle GNSS traces. Further analysis revealed strong correlations between certain GPS parameters, with CN0 exhibiting a correlation of 0.98 with BBCN0, making one of them redundant. Feature reduction was performed using linear discriminant analysis, LDA, which was motivated by the reasonably high correlations between CN0 and other parameters. The authors proposed a machine learning model to classify both ambient settings and human activity, comprising 8 features collected from the phone, with nonlinear noise eliminated using unscented Kalman filtering, UKF. The UKF selectively filtered non-critical noise components, maintaining a balance between noise reduction and retention of essential signal features. Standard scalar normalization was applied prior to LDA to address differing scales and normalize the data. The reduced feature set was then mapped to a class label using a machine learning-based classifier. Notably, the study reveals a strong correlation between AGC and RSS, demonstrates the effectiveness of UKF for nonlinear noise filtering, and showcases the application of LDA for feature reduction. The proposed ambient sensing framework and machine learning model are designed to classify ambient settings and human activity, contributing significantly to the development of accurate and efficient ambient sensing systems. The authors evaluate the performance of 6 machine learning algorithms: random forest, k-nearest neighbor, support vector machine, decision tree, naive Bayes, and gradient boosting for ambient sensing and human activity recognition using semi-processed GPS parameters. To determine optimal hyperparameters for each model, grid search CV is employed, with results presented in Table 3. Notably, the one-vers US1 strategy is adopted for support vector machine to address class imbalance. The learning models are trained on the Google Collaboratory Cloud Platform, utilizing a dual-core Intel Xeon CPU and a NVIDIA Tesla T4 GPU. For ambient sensing, over 100,000 samples are collected in diverse locations, including a dormitory floor, stadium, bustling market, and underground metro tunnel, using 20 volunteers. 5 user environments are defined: flight, indoor, metro tunnel, open ground, and outdoor crowded area. Class labels are determined using precise location coordinates and mapping services like Google Earth. The authors assess the effectiveness of each semi-processed GPS parameter, after Kalman filtering, for characterizing the ambient environment. Individual parameters achieve an accuracy range of 40.6% to 86.7%. To improve results, the authors combine parameters and evaluate model accuracy after applying UKF, scaling, and LDA. Figure 7 shows that random forest and gradient boosting exhibit the best performance, with accuracies exceeding 90% for all settings. Table IV presents results for each setting using popular machine learning metrics, including accuracy, sensitivity, specificity, and F1 score. The evaluation highlights the importance of combining semi-processed GPS parameters to achieve high accuracy in ambient sensing and human activity recognition. The results demonstrate the effectiveness of random forest and gradient boosting in this context, with potential applications in various fields, such as smart cities and IoT. Ambient sensing accuracy for each semi-processed GPS parameter is presented in Figure 6. The performance metrics of the ambient classifier models are shown in Table IV, with gradient boosting, GB, and random forest, RF, emerging as the top models across all metrics, boasting high accuracy, sensitivity, and specificity scores. Notably, the GB model accurately classifies scenarios with nobody present and 2 people present in a small room, achieving an accuracy of 99.25% as illustrated in Figure 8. To evaluate the relative importance of each feature, the authors employed a permutation importance method, randomly shuffling the values of each parameter and measuring the resulting increase in the model's prediction error. The feature importance scores are presented in Figure 9, with a GC exhibiting the highest importance score of 0.78, and all other features contributing substantially to classification with scores ranging from 0.55 to 0.75. The paper then shifts focus to human activity recognition, HAR, where class labels are defined for both static activities, sitting, lying, and standing, and dynamic activities, such as walking, running, or traveling in a vehicle. The Android platform's GetSpeed API is utilized to discern dynamic activities based on speed or velocity, while Doppler shifts captured by the PR attribute are employed to classify dynamic activities. Static activities are categorized into 4 classes: sitting, standing, lying down, and hand waving, mobile phone not held with the moving hand. The proposed approach for human activity recognition, HAR, using fused GPS parameters demonstrates promising results. Classification confusion matrices for 6 machine learning models: random forest, RF, decision tree, DT, support vector machine, SVM, K nearest neighbors, KNN, naive Bayes, NB, and gradient boosting, GB, are presented in Figure 7. Notably, RF and GB achieve the highest accuracy, with 99.9% and 99.8%, respectively, outperforming SVM and KNN. Figure 8 shows that the proposed approach effectively classifies indoor environments with varying population densities. The accuracy of individual GPS parameters is evaluated in Figure 10, revealing that the AGC parameter achieves the highest accuracy of 77.2%. While ADRNG performs poorly with a high misclassification rate of 72.6%. This highlights the limitations of using individual GPS parameters for HAR and underscores the need for combining them to achieve better results. Figure 11 compares the performance of different machine learning models using fused GPS parameters, with RF, DT, and GB achieving the highest accuracy, ranging from 80% to 97.2%, RF. Table V presents the same data along with other machine learning metrics, including sensitivity, specificity, and the FS score, further supporting the superior performance of RF. A feature importance test for ambient classification using the GB model, presented in Figure 9, reveals that the AGC feature has the highest importance score of 0.88, while all other features have importance scores between 0.5 and 0.65. This supports the claim that using fused parameters improves the accuracy of HAR. The results demonstrate the effectiveness of the proposed approach for HAR using fused GPS parameters, highlighting the potential of machine learning models, such as RF and GB, to significantly improve accuracy. Machine learning models, including random forest, decision tree, gradient boosting, K nearest neighbors, naive Bayes, and support vector machine, were employed for activity classification experiments. Performance metrics, comprising accuracy, sensitivity, specificity, and FS score for each activity class, are presented in Table V. The results indicate that the random forest model achieves the highest accuracy for handwaving, lying down, sitting, and standing activities, with values of 77.5%, 97.2%, 91.2%, and 82.7%, respectively. The gradient boosting model also exhibits strong performance, with accuracy values of 82.4%, 96.9%, 86.7%, and 82.8% for the respective activities. Figure 10 illustrates the activity classification accuracy for each semi-processed GPS parameter, providing insight into the model's performance. The robustness of the proposed method was evaluated through several experiments. The impact of varying the number of unique satellite vehicle IDs on prediction accuracy was assessed, and the results in Figure 13 demonstrate that even with a reduced number of IDs, the method achieves an accuracy of 92.1% for ambient classification and 84.4% for activity classification. The effect of different train test splits on model accuracy was also examined. Figure 14 shows that even with a high proportion of test data, the average accuracy of ambient classification is 94.2%, and 85.4% for activity classification. This highlights the resilience of the proposed method, which can be attributed to the unscented Kalman filter's noise removal and feature preservation capabilities. Additionally, the accuracy of the model was evaluated using unseen events, with experiments conducted using different Android phones and settings. The results demonstrate the robustness of the proposed method in handling varying environmental conditions and phone settings. The proposed method is shown to be robust against variations in environmental conditions, SVID density, and train splits. The use of the unscented Kalman filter is found to be crucial in maintaining high accuracy, with a significant drop in accuracy observed when the filter is removed. In the realm of human activity recognition and ambient classification, researchers have conducted experiments to evaluate the performance of various machine learning algorithms using sensor data. The confusion matrices in Figure 11 reveal the accuracy of different classification models, including random forest, RF, decision tree, DT, support vector machine, SVM, k-nearest neighbors, KNN, naive Bayes, NB, and gradient boosting, GB, in predicting 4 classes: hand-waving, lying down, sitting, and standing. The results show that GB and RF outperform other models, with GB achieving the highest accuracy of 80.7% for ambient classification and RF achieving 82.4% for activity recognition. Figure 12 illustrates the feature importance test for human activity recognition, highlighting the significance of acceleration, state, and other features in the classification process. To assess the robustness of their approach, the authors conducted experiments by collecting data at different locations, including a cruise ship, and varying the number of unique sensor IDs, SVIDs, and the train-to-test ratio. The results, presented in Figures 13 and 14, demonstrate that the accuracy of the models remains consistently high, above 91.5% for ambient recognition and 83% for activity classification, despite the changes in experimental setup and data. The decrease in precision observed in these experiments is attributed to variations in multipath effects and the different experimental setups. The best performing techniques, GB for ambient classification and RF for human activity recognition, remain consistent across different scenarios. Overall, the results demonstrate the effectiveness of the proposed approach in human activity recognition and ambient classification using sensor data, and its robustness to changes in experimental conditions. The study evaluates the accuracy of ambience and activity classifications performed by random volunteers at various locations, as shown in Figure 15. Ambience classification generally outperforms activity classification, with the highest accuracy achieved for the indoor class at 94.0%. However, activity classification accuracy is influenced by phone model variability and environmental conditions, resulting in an 8% difference between 2 Redmi Note 9 Pro Max models from different build years. To address these issues, the authors applied the unscented Kalman filter, UKF, followed by linear discriminant analysis, LDA, reducing the maximum accuracy difference to 3% for data logged at the same time and 4.2% for data logged at the same place but at different times. This highlights the effectiveness of their approach in handling noisy readings across diverse phone models and ambient conditions. The study then focuses on determining the indoor floor layout using semi-processed GPS data. Prior research has utilized Wi-Fi RSSI, user activities, and graph optimization techniques to construct indoor maps, but these methods are not applicable to GPS signals. The authors propose leveraging GPS RSSI as a starting point and building upon it, despite its limitations. To investigate GPS RSSI variations across different areas of a large indoor space, the authors conducted an experiment in a dormitory corridor measuring 32.3 meters times 25.6 meters. They generated a heat map depicting the relative GPS RSS levels across the site using NetSpot, a commercial tool designed for Wi-Fi signal strength mapping. The heat map clearly identifies points of interest such as lifts, stairs, and rooms, but the data does not provide information on what is located at these points. To address this, the authors propose a trajectory creation methodology using location data and activity landmarking. They aim to identify floor landmarks such as pathways, stairs, elevators, rooms, and obstructions based on user activity and GPS BASED location information. The authors employ their human activity recognition (HAR) framework to capture user activities, which can be used to identify landmarks. The methodology involves creating a trajectory of user movements using GPS location information and activity data. The authors suggest using the GPS location information to identify the user's location and activity, and then use this information to create a trajectory of the user's movement. This trajectory can be used to identify landmarks such as pathways, stairs, and elevators. The study emphasizes the potential of utilizing semi-processed GPS data to create indoor floor maps, despite the challenges posed by GPS signal noise and variability. The authors demonstrate the effectiveness of their approach in mitigating these issues and propose a methodology for creating indoor floor maps using GPS data and activity landmarking. Researchers have developed a novel approach for generating indoor floor maps using semi-processed GPS data collected from multiple users' smartphones. This method combines GPS signals and human activity recognition (HAR) to identify and classify landmarks such as stairs, lifts, rooms, and empty corners within a site. The process begins with collecting GPS data and HAR fingerprints from volunteers who traverse the floor, starting and ending their journeys at random points. This data is then used to create an initial map, which undergoes alignment and optimization processes to refine the locations of activity landmark points. In evaluating the accuracy of classifying these activity landmark points, Random Forest, RF, shows strong performance with an average accuracy of 90.15%, followed by Decision Tree, DT, and Gradient Boosting, GB, with average accuracies of 87.5% and 87.7%, respectively. K-nearest neighbors, KNN, and naive Bayes, NB, have moderate and adequate performances, while Support Vector Machine, SVM, has the lowest average accuracy of 50.2%. To assess the quality of the generated map, metrics such as Graph Discrepancy Metric, GDM, and Shape Discrepancy Metric, SDM, are employed. The results indicate that the maximum error observed is 4.10 meters for GDM, with the 90th percentile error being 3.42 meters. Similarly, for SDM, the maximum error is 3.41 meters, with the 90th percentile error being 2.94 meters. These findings align closely with related work, validating the efficacy of the proposed method in constructing floor maps. The research also highlights potential privacy risks associated with the exploitation of Android applications that access semi-processed GPS data. To mitigate these risks, Android 12 introduces a privacy option allowing users to choose between fine and coarse location permissions, thereby enhancing user control over location data access. Users of Android 11 and earlier versions are advised to carefully review app descriptions for fine location requests. Semi-processed GPS data, widely available on Android devices, poses significant privacy risks due to its vulnerability to exploitation. Despite the need for location-based services, disabling fine location permissions is not a practical solution, as users are often unaware of the associated privacy risks. Related work in ambient sensing and human activity recognition has explored image-based solutions, as well as wireless signal patterns such as Wi-Fi channel state information and received signal strength. However, these approaches rely on GPS coordinates or other location information. In contrast, this study introduces a novel approach that utilizes semi-processed GPS signal parameters to categorize events without relying on GPS coordinates or location information. This approach leverages the widespread availability of semi-processed GPS data to develop a privacy-preserving method for event categorization. The proposed method is based on the extraction of meaningful features from semi-processed GPS signal parameters, which are then used to train machine learning models for event classification. This approach is particularly significant, as it enables the development of privacy-preserving location-based services that do not compromise user privacy. The research highlights the importance of addressing the privacy risks associated with semi-processed GPS data and demonstrates the potential of leveraging this data for event categorization while preserving user privacy. A comprehensive comparison of event classification approaches and indoor layout mapping methods reveals the advantages and limitations of existing research. Table 7 summarizes the comparison of event classification approaches, highlighting the use of diverse signals such as Wi-Fi, IMU, cell tower, GPS, RFID, and camera. Notably, the current approach, AndroCon, does not rely on Wi-Fi or assisted GPS signals, unlike other studies. In contrast to Bui et al., 64, and Zhu et al. 65, who utilized processed GPS signals to classify ambient conditions with less accurate results. AndroCon encompasses diverse settings not accounted for in previous studies. A comparison of related studies on indoor layout mapping, primarily employing simultaneous localization and mapping, SLAM, a computer vision technique, is presented in Table 8. Conventional SLAM techniques depend on visual cues, such as landmarks, camera-detected obstacles, sonar data, or laser-range sensors, which may incur high costs or raise privacy concerns. Alternative methods, including crowdsourced user trajectories, Wi-Fi RSS fingerprints, Bluetooth and Wi-Fi data for trajectory alignment, and pedestrian movement traces, have been proposed, but they have limitations, such as sparse Wi-Fi access point deployment or challenges in accurately representing curved features within the maps. The current approach draws inspiration from Zhou et al. 50, which leverages Wi-Fi RSS and MAC address fingerprinting for trajectory alignment and landmark identification. However, AndroCon utilizes semi-processed GPS data and does not require any other information, unlike Zhou et al.'s method, which relies heavily on mobile sensors and requires extensive user permissions. The discussion highlights the advantages of methods utilizing M-waves, such as Wi-Fi, Bluetooth, or GPS, over image-based solutions, which raise significant privacy concerns. AndroCon provides similar accuracies to camera-based designs without compromising user privacy. The approach has been extensively tested with a large dataset, demonstrating robust results. The method can construct floor maps with a maximum error margin of 4.1 meters compared to the ground truth and classify points of interest within an indoor layout with approximately 90.15% accuracy, relying solely on GPS data. The identified vulnerability and use cases, excluding the floor mapping use case, have been reported to the Android security team, ensuring responsible disclosure. Here's a comprehensive comparison of indoor floor mapping approaches, showcasing the methodologies employed by various researchers. A summary of key aspects is presented in Table 8, which highlights the utilization of sensors, GPS, and Wi-Fi. Notably, most approaches combine sensors and Wi-Fi signals to achieve accurate indoor mapping. Sensor-based approaches, such as those leveraging lidar, stereo cameras, and inertial measurement units, provide high-resolution 3D point clouds and accurate distance measurements. Meanwhile, Wi-Fi-based methods, including fingerprinting and trilateration, utilize received signal strength indicators to estimate device locations. Hybrid approaches, which combine sensor and Wi-Fi data, offer improved accuracy and robustness. Several researchers have employed machine learning algorithms, such as Gaussian processes and random forests, to refine indoor mapping models. These algorithms enable the integration of heterogeneous data sources and improve the accuracy of location estimation. Table 8 reveals that GPS is rarely used in indoor floor mapping due to its limited availability and accuracy indoors. In contrast, Wi-Fi signals are ubiquitous in indoor environments, making them a popular choice for indoor mapping. While this comparison highlights the strengths of various approaches, it also underscores the need for further research to address the limitations and challenges of indoor floor mapping, including multipath effects, signal attenuation, and device heterogeneity. Future work should focus on developing more robust and accurate indoor mapping methods that can generalize across diverse environments and devices. I'm ready to refine the transcript. However, I don't see the original content provided. Please paste the transcript you'd like me to refine, and I'll get started. I'll follow the guidelines you provided to transform the text into a concise, technically accurate summary suitable for voiceover narration.